In this video, we're going to learn about slope fields for first-order differential equations and how they help us visualize how solutions behave without having to solve the equation. We'll learn how to construct slope fields and solution curves and walk through 3 examples so you can see the different types of solutions you can have. Let's start by looking at a first-order ordinary differential equation. On the left, we have a first-order derivative, and on the right, we have a function of x and y. We also have an initial condition that tells us that the solution y of x passes through the point x0, y0. The solution curve that we're going to be constructing is just the graph of the solution y. At any point on the graph, the slope of the solution curve is given by the right-hand side of our equation, which can be a function of x and y. The nice thing is that f of x and y is given to us in the original equation, so we don't have to solve this equation for y to know what the slope of the solution is. Since the slope can depend on x and y, it may change for different values of x and y. A slope field is just a collection of these different values that are short line segments drawn at selected points, x, y, each having a slope f of xy. Let's look at an example to see what this looks like. Over here on the right, we have a differential equation dy dx is equal to minus y, along with an initial condition y of 0 is equal to 2. In this example, our slope doesn't depend on x and only depends on y. To start, let's compute some slope fields. When y is equal to minus 2, the slope dy dx is minus y, which makes it equal to 2. Let's plot that. Let's go down to y is negative 2, and I'm going to highlight these lines so that you can see that these lines indicate that the slope is equal to 2. When y is negative 1, the slope is 1, and then when y is 0, the slope is 0. Let's plot those. When y is 0, our slope is 0, so our slope fields are just horizontal lines. When y is 1, our slope is negative 1, and then when y is 2, the slope is negative 2. Let's plot those. We go up to where y is 2, and you can see that our slope fields have a slope of negative 2. Once all the slope fields are drawn, we can use the initial condition y of 0 is equal to 2, right up here, to sketch a solution curve. Let's plot x is 0, y is 2. That's our point right here. And then you can see that we have a solution curve drawn that follows those slope fields and passes through that point. You can see from the graph that we can understand the qualitative behavior of our solutions without even solving the equation. Before we go on, I want to make a note about one thing. Sometimes, instead of line segments, you can use vectors to show the direction of the solution. When you use vectors, instead of saying that you have a slope field, you're going to be talking about a direction field. It's the same thing as the slope field, except you have vectors instead of line segments. Let's look at some examples where we are going to construct a slope field for the given differential equation and use it to sketch an approximate solution curve that passes through the point that we're given. Let's look at our first example. We are given the slope dy dx is equal to minus 2y, and the initial condition y of 0 is equal to minus 2. Since the slope dy dx only depends on y, we need to start by finding the slope for different values of y. When y is negative 2, our slope is minus 2 times minus 2, which gives us a value of 4. Let's go over to our graph and let's plot this. When y is equal to negative 2, our slopes have a value of 4. I plotted this slope field on Desmos. It's a free graphing calculator, and it produces really nice slope fields. Let's now go back to our table. When y is -1, dy dx is going to be 2. When y is 0, we get 0. When y is 1, we get -2, and then we get -4. Let's plot what some of these fields look like. When y is -1, we have a slope of 2, so our line looks like that. At 0, it's equal to 0, so we have a horizontal line. At 1, it is -2, and then at 2, it's equal to -4, so our line is steeper. Notice that in our graph, the slope fields are the same for every value of x. That's because our function is equal to -2y and doesn't depend on x. Let's also notice that the slopes are negative for points above the x-axis, and they're positive for points below the x-axis. Let's now plot the solution curve that corresponds to the initial condition, y of 0 is equal to -2. We let x be equal to 0 and y be -2. That's this point right here. And then we can just plot the solution curve based on these slope fields. As we move to the right, our solution curve is going to move toward the x-axis. It's really great that we can see what our solution looks like without even having to solve the equation. Let's now look at our second example. I wanted to do this one because it's different from our first example because our slope is equal to a function of x and y. Because of this, our slope field is a little bit more complicated. You can already see that by looking at this graph. And then calculating the slopes is also more complicated because we have to consider x and y. Down here on the left, I have written our x values from -2 to 2, and then our y values, and I chose them to be from -2 to 2 as well. Let's go ahead and fill in this table. When x is -2 and y is -2, we're going to have -2 minus a -2, and that gives us 0. When y is -1, we're going to have -2 plus 1, and we get -1, and then likewise, we're going to get -2, -3, and -4. You just need to follow that process to fill in the rest of the values. Here's those values. Let's plot 3 of these slopes. Let's first plot this slope. X is -2, y is -1, and our slope is -1. Now let's plot this value. X is 0 and y is 0, so that's right at the origin, and we're going to have a horizontal line to indicate that our slope is 0. Let's now plot this slope. X is 2, y is 1, and our slope is equal to 1. Notice from our graph that the slopes are different on the left and on the right. They're not the same as they were in example 1, and the reason for that is because our slope depends on x and y. So it's going to be different for different x and y values. Let's now draw the solution curve that passes through the point x is -2, y is 0. That's our initial condition. When x is -2, y is equal to 0. That's this point right here. And our solution curve is going to look like this. As we move toward the right, our solution is going to move toward the line y is equal to x. Let's now look at our third example. This one is different from our first 2 examples because our slope, y squared minus 1, is a nonlinear function of y. This is going to lead to some really interesting solution curves. Let's start by finding the slope for different values of y. When y is equal to -2, our slope is -2 squared minus 1, which is 3. When y is -1, we get 0, and then we get -1, 0, and 3. Since our slope is only a function of y, notice in the graph that the slope fields are the same on the left and the right. They're going to be the same for every value of x. Let's go ahead and plot the values that we just computed. When y is -2, our slope is 3. That's these lines right here. When it's -1, we have 0. So at -1, we're going to have horizontal lines. When y is 0, our slope is -1. That line's going to look just like this. When y is 1, we again have horizontal lines. And then when y is 2, our slope is 3, so it's going to be steeper. And those lines look just like this. Notice on our graph that we have 0 slopes when y is equal to -1 and when y is equal to 1. Those are actually called equilibrium solutions, and I'll talk about those types of solutions in another video. Let's look at the 3 regions. In the region on the top, all of our slopes are positive. In the region between our 2 equilibrium solutions, our slopes are negative. And then in the region on the bottom, our slopes are positive again. Because our slope is nonlinear, we are going to get different solution curves for different initial conditions. And that's why for this problem, I've written down 3 different initial conditions. Let's look at the first one. Y of 0 is equal to 0. That means we're going to start right here at the origin, and our solution curve is going to look like this. It's going to start on this line, and it's going to come down, and then end on that line. For our second initial condition, we have y at 1 is equal to 2. So when x is 1, y is 2. That's this point right here. And the solution curve that passes through that point is going to look like this. It's going to start on the line y is equal to 1, and then come up and increase toward the right. Now let's look at our last condition. That one is y at 1 is equal to -2. So when x is 1, y is -2. That's this point right here. This solution curve looks like this. We're going to start down here, come up through that point, and then we're going to end on the line y is equal to -1. It always works out that when you have a nonlinear slope, different initial conditions may produce different qualitative solution curves. And that's it. You now know how to use slope fields to visualize solution curves and understand the different types of behavior solutions to first-order differential equations have without having to solve the differential equation.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.